Thank you. So I will do this in English, if that's okay. Yeah, so I'm very happy to present sort of an overview of some of the work that we've done in my chair since 2019. So the chair was called Deep Learning with Semantic, Cognitive, and Biological Constraints. And I had the chance to have as co-chairs experts in language from IRIT, in neuroscience from CERCO, and experts in mathematics from IMT. And so some of the things I will present are some of our efforts to use deep generative networks to improve our ability to decode brain signals. Then I'll tell you how the other way around, we also try to use neuroscience, and in particular a theory called predictive coding, to improve neural networks for computer vision. And in the same line, how we used another theory called global workspace theory to improve multimodal systems. And this is both the topic of a recent ERC project in my lab and the inspiration for the synergy chair proposal that we submitted for the new version of ANITI. So there's still a question mark here. So I will say a few words about this at the end. So let me dive right in. So what is brain decoding? Basically what we do is we show images to the subjects when they're lying in an MRI scanner, and then we record their brain activity, and then we try to learn a mapping between this brain activity and the latent space of a deep generative network, so that later we can use this mapping on new images, new brain activation patterns that were not part of the training set, to guess what image the subject is looking at. So these are the guesses corresponding to these images here. So we've been doing this for a while now. We were among the first to do this in 2019. And we sort of followed the evolution of deep generative networks over time. So back then, in 2019, we did it with faces using VAEs, variational autoencoders. Then in 2022, we did it with natural images using GANs, Big GAN, IC GAN. And more recently, we just published a report where we do this on using a diffusion model, because that's what works best nowadays. And so I'll say a few words about this. It's called Brain Diffuser. And it's the same idea. What we do is first we learn the mapping between brain activation patterns and the conditioning vectors that people would typically use, either image conditioning vector or text conditioning vectors that people would typically use to condition a stable diffusion image generator. And once we do this, once we've done this learning, then we use this mapping on new images, new brain activation patterns. We try to predict what should be the conditioning vector, both for images and text, and we use these conditioning vectors to condition the image generation process and reconstruct an estimate of the image the subject was looking at. So these are 8 examples of the reconstructions that we got. Original image on the left, image reconstructed on the right. It's not perfect, but you can always sort of recognize what's in the image, where are the objects, and so on. And this is actually the state of the art in brain decoding, or in this mind reading technology, if you want, nowadays. So that's a fun neuroscience application, I would say. But we don't just use neural networks to improve brain science. We also try to do things the other way around. We try to use our knowledge of the brain to improve neural networks, for example, in computer vision. So typically, computer vision models work in a feed-forward way. From the image, you send information through a series of successive layers, typically convolutional layers, it might be transformer layers nowadays, until you get to a decision layer, where you can make a classification. And so these feed-forward networks are also typically trained in a supervised way, where you know for each image what is the answer that you want the network to give, and you force the network to learn the right mapping. So these work extremely well. They have very good performance, but they are not very robust. They tend to be susceptible to noise, corruptions, and so on, adversarial attacks. We heard about this this morning. And also, it's not very biologically plausible, because we know that in the brain, of course, information flows in the feed-forward direction, certainly, but there's also a lot of feedback loops in the brain that go from the higher brain regions down to the lower brain regions. And so we wanted to see whether we could include these sort of feedback loops in these computer vision systems. And so we choose a theory from neuroscience called predictive coding that tells us a little bit what the feedback should be doing. So what we did is we started from a feed-forward vision backbone, a pre-trained model, typically on ImageNet, and we just added a separate stream, a feedback stream, that would implement this predictive coding. So basically each layer, that's the red arrows that you see here. I don't know if you see the difference between red and black, but the red arrows implement feedback predictions that each layer is making about what's coming from the layer below. And then we can compare these predictions with the actual representation at each level. And then we can send this error signal to the next layer so as to minimize this prediction over time. So basically what we do is we combine two streams, a feed-forward stream, which is a discriminative network for classification, and a feedback stream, which is basically a generative network. It's trying to reconstruct the input. And both streams, over time, are going to update until they come to an agreement, and hopefully this agreement will be a better interpretation of the input. So in practice, this is how we implement it. In addition to the standard feed-forward input drive that would correspond to the green arrows, we also have the prediction mechanism and the error correction mechanism implemented by all the other arrows. This looks a little bit complicated, but we try to make life easy for everyone by providing a software that does it. You can download this. And basically what this software does is you can start from any backbone, any pre-trained model that does the feed-forward pass, and you can augment it with the feedback loops that will do the predictive coding and that you can train in an unsupervised way. And so we played this game with various backbones, VGG, EfficientNet, ResNet, and so on. And so what do we find in terms of performance, for example, on the ImageNet dataset? These are two examples with VGG and EfficientNet. So each time what you see here is that the feed-forward accuracy is represented at time 0. So that's your baseline, if you want. That's one feed-forward pass to the system. And as the time steps evolve, then you get more and more predictive coding inside the system. And so what do you gain by doing these predictive coding steps? Well, actually, you don't gain much. You might even sometimes lose a little if your input is nice and clean. So that's the blue lines here. Those are for clean images. But predictive coding is really helpful when your input is corrupted. So here the different colors correspond to different amounts of Gaussian corruption that we added to the signal. And you see that over time, the predictive coding iterations can restore a good performance, sometimes up to 6 percentage points. And indeed, if you look at the input image, the corrupted input image given to the network, and at the reconstruction of the image, as seen from the network after 10 time steps. So by the way, one advantage of working with generative networks is that we can always reconstruct the estimate of the input as seen from the network and inspect it to try to understand what's going on. And what we see is that clearly there is some denoising going on. But the network is not trained for denoising, it's trained only on clean images. So somehow it has figured out how to remove the noise by projecting the images on the manifold that it has learned, the manifold of clean images. So in short, with these predictive coding networks, we get some robustness, not only to Gaussian noise, but also to other corruptions. We tested the network on the whole ImageNet-C corruption benchmark. And we showed that we also have some robustness to adversarial attacks, which is quite helpful. And I don't want to spend too much time on this, but it's not only a quantitative improvement, but it's also a qualitative improvement. So for example, we could show that these networks tend to perceive perceptual illusions very similarly to humans. This is an example of an illusion where humans see a square on top of these black inducers, even though there is no square. Typically, feed-forward networks would not detect a square here, but the predictive coding networks do. And also, very briefly, we just published a paper on the mathematical convergence of these predictive coding systems. Under certain assumptions, we have some guarantees on the conditions in which these networks will come to a final solution. Okay, and to finish, I also want to describe how we applied the same logic not to computer vision systems, but to multimodal systems, trying to improve them with brain inspiration or brain-inspired theories. So it's a tall order, of course, because multimodal systems are getting really good these days. You might have heard of CLIP, DALI, and so on. So these networks would typically combine vision, language, sometimes even action. And they're really good at what they do. If you've ever played with DALI, it's quite impressive. But they are typically very large models. Well, they're typically closed models also. That's another problem. And they require really gigantic training sets and typically supervised training sets. So for example, DALI was trained with billions of pairs, each time with the image and a corresponding text description for that same image, billions of them. So that's not really frugal. And that's really not how the brain does it. And so, of course, we don't really know how the brain does it, but there is a theory about how the brain integrates information from different modalities. It's called the global workspace theory. And so we wanted to use this theory. So in a nutshell, what it says is that the different domains in the brain, the different modalities, are combined into one common representation, the global workspace. And then this common representation is redistributed to all the other parts of the brain. It's called a broadcast, the redistribution of this joint representation. And so we wanted to try to see if having this global workspace in a multimodal system could improve things. Of course, we're not OpenAI or Google, so we're not going to do this on natural images. So we did it so far on a simple data set where we just have simple geometric shapes and their description in English. So this one, for example, would be a little yellow-green bullet located at the center, pointing towards the northeast. And what we want to do is learn a mapping between these two domains through a global workspace architecture. So it's a simplified architecture, of course. What we have is a visual stream and a language stream. The visual stream is based on a VAE, a variational autoencoder architecture, to extract latent features from each of our images. And that is pre-trained and subsequently frozen. We're not going to learn this. It's just a given. And we have the same thing on the language side. We have, on the language side, we have a pre-trained BERT model to extract features, linguistic features from our captions. And this is frozen. And now what we want to do is learn somehow a mapping between these two domains through a global workspace representation in the middle. So what we have to do in practice is learn to encode information from, let's say, images to the global workspace and learn to decode them, and the same from language. And so these are basically neural networks that we're going to train. How do we train these neural networks? There's different ways of doing it. There's the standard way. If we have access to matching pairs, each time with the image and the captions, just like in DALI, they had billions of them. But if we have n of them, then we can apply standard supervised training methods. We can start from the image, we can turn it into a linguistic vector, and we can compare to the ground truth. Or we can start from the language, turn it into an image, and compare to the ground truth. And we can optimize this. And we can vary the number n to see really how many labels, how much supervision do you need for this task. But because we're working with this global workspace architecture, we also have another way of doing the training based on the simple idea of cycle consistency, or also based, if you want, on the idea of broadcast that is important in the global workspace. This idea that if you send information into the workspace, then you should be able to redistribute this information back into each of the other modalities. And that tells you that you should be able to optimize this even when you don't have paired data, even when you don't have ground truth matching. For example, you could start from an image vector, you could send it to the workspace, and you should be able to come back to the same place. And you don't need matched data to do this. Same coming from language. You can go to the workspace and come back. And you can even do one step further. You can go from an image to a linguistic description. You don't know what's the ground truth here, but you can always come back. And logically, you should come back to the same place. And the last one, finally. So importantly, you can do all this training only with unpaired data. unsupervised, and so you don't need all these large data sets. So we tested this idea on our simple data sets with our simple architecture with just 2 modalities, and this is what we found. So we're measuring the translation error, so down is better on this graph, the translation error between the 2 modalities, vision and language. If we do this the standard way, the supervised way, that's the blue line, you see that, well, eventually, if you have enough data, of course, you'll manage to do this. You need about 100,000 examples of image and caption to do this task properly. But if you apply our idea with the broadcast and the unsupervised training, then you can actually do the same thing with a lot less data, approximately, on average, 7 times less data to get to the same performance level. So that's definitely a lot more frugal way of learning. And we just submitted a paper with these results. You can find it on arXiv. So this is where we are now. We have this simple bimodal version of the global workspace that was trained between these simple shapes and these sentences. You don't need to use actual language. You could use even simplified language where you just give a vector with a description of the attributes. That also works. And by the way, that was the work of Benjamin de Villers, who was a PhD in INIT, and now he's a postdoc in the lab. More recently, Léopold Métier tried to do the same thing in more realistic environment, robotic environments. For example, in this environment, I don't know if you can see very well here, but we have a robot moving around in simulation, of course. And there can be a table anywhere in the scene, and we can learn a mapping between the camera image from the robot and the actual attributes of the scene. And so that's fairly interesting for robotics, because that means now we have this mapping. If you give me the camera image from the robot, I can tell you exactly where is the robot, what's in front of it, what are the properties of the table, and so on. And vice versa. If you give me a list of attributes here, I can sort of picture the scene as it would be from the point of view of the robot, even without actually running the simulation. And we also have a final version of these simulations with a much simpler simulation environment, a very simple arena with 4 walls and nothing in between. But this is important for us because we actually want to take this to the lab with our partners in the LAS and actually go from the simulation to a real robot, a solo robot, because in the LAS they have exactly this environment, and we can see if our simulations will generalize in reality. So this is where we are and where we're going. Well, as I said, this work was started in INIT, but it will continue as part of an ERC project that just started in September, where we're going to continue to develop these sort of brain-inspired multimodal systems. And hopefully we can find their usefulness, their relevance for machine learning, and they should also help us advance our knowledge of the brain. And this idea is also the basis for our chair proposal that we submitted to the new version of INIT, still with question marks here. It's called C3PO for cobots with conversation, cognition, and perception. It's a synergy chair, so it's actually 4 chairs into one. In addition to myself, there will be Nicolas Ascher, Thomas Serre, and Olivier Stas from the LAS. And so with our combined expertise, what we want to do is to create more advanced, more elaborate versions of our global workspace with vision, language, robotics, movement, and so on. In other words, to provide frugal multimodal robots with grounded perception, grounded language, action. And this should be of interest to our industrial partners, mainly Linagora and Airbus, that we're already collaborating with. So thank you.
How much do we need to optimize I mean, the architecture of those networks? I understand that the key point is really having this global workspace, but and you use, I don't remember for the language, it was something pretty simple.
Yeah. Yeah, so if I can go back, let me get 2 slides, 3 slides in the back. So I think the question is, these these sorts of networks, these encoders and
does it matter
decoders.
very much for performance, or you
Yeah,
learn
actually,
already quite a lot?
no, we didn't play around too much with this. We use, I think Leopold tried, basically there's some hyperparameter optimization. So if they're too small, it doesn't work. And if they're too big, it overfits and you can't train the models. And there's always an optimal. But it, I mean, typically we use 3 layers and a couple hundred neurons in each layer, and it works. But it depends on the data set. So far, we've only been playing with small data sets. So when we move to bigger data sets, probably it can't be too simple, but we don't have the compute to do that.
It seems it's really a good idea to do that, and then it's less important. Excellent. Other questions? Yes, Michelle.
Yes, thank you. The question about the same slide. If you don't have the pairing, I mean, if you have just the
If you don't have the pairing at all, it also doesn't work. So you need some amount of pairing, and I think it makes sense. When you think of it, you're trying to learn, well, we know actually because this is controlled, right? So there's a bijection that exists between the visual space and the language space because we control everything, right? But the number of bijections that you could find between two spaces like this is infinite. Well, it's not infinite, but it's extremely large, right? And if you don't have, if you're just trying to learn a mapping back and forth, any bijection would do, because you go to one space, you come back. As long as you come back in the same space, you have cycle consistency. And we need a few anchor points to find the right bijection among all these possible bijections.
Yeah.
And so that's what the graph shows. If you have basically 1,000 points, then you have enough to control, which of the bijections is the right one. But if you don't have any, then you're screwed.
The question is exactly this. I mean, could you replace anchors with properties? For instance, the fact that you have, say, a kind of property and with different frequencies.
Yeah, so for example, yeah, I think I agree with you. It's first because we design our space to be bijective and to be uniformly sampled across all properties. It's easy to exchange properties, and that's where the problem is. If there's something that tends to occur a lot more often in each domain, then it's likely that it's matched, right? Yeah. And that could provide additional information. So we don't have that, but it could be an additional source information, and it should decrease the need for supervision. So it should help us. That's true.
Thank you. So if no more questions, let's thank Rufin and move on.